You would have known that there are three main types of conic section: a parabola, an ellipse, as well as a hyperbola. Now, they all have their own geometrical properties. And you'll be wondering, why are these three types of conic section actually a family of curves? Because they seem so different. Now, I'm going to introduce to you this new term known as eccentricity. And eccentricity itself is sufficient to describe each type of conic section, meaning it gives it a unifying definition. Now, eccentricity is actually a ratio of PF and PD, where PF represents the distance from a general point P on a conic section to a point called F. And PD is the distance from that point P, which is on the conic section, to a fixed line called D. And the three types of conic section has different values of eccentricity. Given a parabola, if we can find a special point F and a special point line, and when we work out what is the eccentricity, it is always equals to 1. Whereas, given an ellipse, we can find a special point F and a special line D, such that the eccentricity is always between 0 and 1. Whereas for a hyperbola, we are able to find a special point F and a special line D such that the eccentricity is always more than 1. Now, this special point F and this special line D has a name. The special point F is also known as the focus, and the special line D is known as the directrix. Now, in the later videos, I'll be showing you how to go about finding this special point and this special line. For now, we just give it a name called F and the line is called D. Now, I'm going to demonstrate to you that this is true. So suppose if I consider a parabola. So let me get a point that is on this parabola and let me call this point P. Now I have a point F and a fixed line D over here, and I will try to find what is the eccentricity. Now this fixed point and this fixed line is very special and they're specially chosen, which, as I mentioned in the later videos, I'll tell you how to go about choosing them. Now I'm going to draw a line segment connecting P to F and P to D. And I'm also going to calculate what is the eccentricity. That is, as you can see from the cursor, is actually PF over PD and is denoted by ECC. For now, because PF and PD is equal, that's why my ECC is equals to 1. Now you'll be saying that maybe it's because I choose a very special point P on the parabola that resulted in the eccentricity being 1. This is not true because as I move my P along the curve, no matter where is it, my PF is always equals to my PD, which result in my ECC or eccentricity being 1 all the time. So observe how my ECC changed. Nothing changed. It's always a constant 1, no matter which point I pick on the parabola. How about ellipse? Let's do the same thing. Let me identify the line called D and a point called F, and let me pick a point that is on my ellipse. Let's call it P1, and let me construct the two line segment. One is P1D, that is the distance between my fixed line and a point that is on my ellipse. and the distance P1F, which is a point on my ellipse, to the fixed point F. So same thing, I need you to observe ECC1, which is actually the ratio of P1F and P1D, which is the eccentricity of the ellipse. Now for now, it seems that the eccentricity is 0.87 for this particular point. But I'm going to show you, no matter where is P1, as long as it is along this ellipse, your eccentricity is going to be constant. Now notice your P1D and P1F, the value keeps changing, but your ECC1, which is the eccentricity, does not change. Okay, now some of you will say that, oh, maybe it is true only for the upper curve of the ellipse. What about the lower curve? Now, because of the restriction of this app, I will have to construct another point, but this time round, this point is going to be something that is on the lower half of the ellipse. Okay, and the same thing, I'm going to draw the two line segment, one connecting the fixed point F to this point P2, and P2 now to the line D. Okay, and the distance is all reflected here, and the ratio is actually represented by ECC2. And again, as my P2 moves along the lower curve, notice my ECC2, the eccentricity, does not change. It remains at 0.87. Okay, so this is, as I mentioned, for an ellipse. You are able to find a fixed point F, a fixed point D, a fixed line D, such that the eccentricity is constant and it is always between 0 and 1 for an ellipse. So last but not least, let's look at hyperbola. Is it also true? Now, of course it is. Okay, now I'm going to pick a point that is on the right arm of my hyperbola. And again, I'm going to construct the two lines, P1 connecting to my fixed line, P1 now connecting to my fixed point called F, and the eccentricity is calculated under ECC1. So again, notice that as I move my P1 along the hyperbola, observe what happens to ECC1. So if I move further down, notice ECC1 doesn't change, it's fixed at 1.12. Even if I move upwards, ECC1 does not change, it remains at 1.12. Now same thing, you'll be asking, maybe it is true only for the right arm of the hyperbola. How about the left arm? Now, so I'm going to choose a point that's on the left arm, and I'm going to connect this point P2 to my fixed line D and to my fixed point F, and then I am going to calculate the eccentricity denoted by ECC2. So I'm taking the ratio of P2F and P2D. Now notice that as my P2 moves along the left arm of the hyperbola, again my ECC2 is a constant at 1.12. It does not change. Okay? So let's go back to the slide. So what I have shown you is true if I pick a parabola or an ellipse or hyperbola. I am able to find a special point and a special line to allow me to calculate the eccentricity, which is constant, and depending on which type of conic section, the eccentricity could be 1 or between 0 and 1 or more than 1. So this also allows us to construct any type of conic section that we desire. So how do we go about doing that? If you want to construct a conic section, all you need to do is to find a point F on the Cartesian plane, as well as construct a line called D. All you need to do is just trace out all the point P such that PF divided by PD is equals to the eccentricity that you want. So for example, if you want a parabola, then you set that ratio to be equals to 1. If you want an ellipse, then you set that ratio to be between 0 and 1. If you want a hyperbola, then set the ratio to be more than 1. And that will give you the conic section you desire.